Hi everyone. I'm going to be going over question 10.15 from the bingo problems. This problem says a wheel rotates without friction about a stationary horizontal axis at the center of the wheel. A constant tangential force equal to 80 newtons is applied to the rim of the wheel. The wheel has a radius of 0.120 meters. Starting from rest, the wheel has an angular speed of 12 revolutions per second after 2 seconds. What is the moment of inertia of the wheel? So I've already gone ahead and written down what we already know, just to save some time so you're not just watching me write stuff down. But the first thing we're going to want to do here is we want to find the angular acceleration. Because that'll help us find the moment of inertia later. And so what we're going to want to do for that is use one of our equations. It says the final angular velocity equals the initial angular velocity plus the angular acceleration times time. And from here we can solve for the angular acceleration. So we end up getting that the angular acceleration equals so here's our formula. I guess we could have just gone straight here since that's the definition of acceleration is the change in velocity over time, but it's fine. I like to do it this way just to get practice manipulating equations. So from here we can solve everything. So we know that first of all, we're going to need to convert our final angular velocity, because it's in revolutions per second, but we need it to be in radians per second. And so we do that, we know 12 rev, 1 revolutions equal to 2 pi, cancels out revolutions, we get 12 times 2 pi, which is 75.4 radians per second. So I'm actually just going to rewrite that up here so that I'm not tempted to write the 12 again. So it's 75.4. Okay, so now we can plug that in. So we know that angular acceleration is 75.4 radian per second minus 0, since that was our initial. And that's because it starts from rest. So of course if it's at rest, it's not moving, doesn't have any angular velocity. And now the time is just going to be 2 seconds. And we'll end up getting that the angular acceleration is going to be 37.7. And this is going to be radians per second squared. So now we have the angular acceleration. So let's write that up here. So acceleration all right. So next we're going to need to use 2 of our torque equations. And so we know that torque is equal to R times F sine the angle. We know the angle is going to be 90 degrees because of how our force is working out. Sine of 90 is just 1, So really it's just going to be RF. And then we also know that the torque is also equal to the moment of inertia times the angular acceleration. Since both of these are equal to the same thing, we can combine them, and we end up getting that the moment of inertia times the angular acceleration equals the radius times the force. Now that we have that, we can solve for the moment of inertia, because that's what we're really looking for. So that we end up getting that the moment of inertia equals r times f over alpha. So now we can just plug in everything that we know. So we know, so I is equal to the radius, which is 0.12, times the force, which is 80 newtons, times that angular acceleration, which we found in that previous part, radians per second squared. Up here, this is meters. And when we figure that all out in the calculator, we end up getting about 0.25. And of course that's kilograms times meters squared. So that's how you find the moment of inertia. As a recap, first of all, we found the angular acceleration. Then we combined these two torque equations, solved for the moment of inertia, plugged everything we knew in, and that we were given 0.25 kilogram meters squared. So anyway, that's the answer to this one. Hope you enjoyed watching, hope you learned something, and I'll see you in the next video.